industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Bonisores, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times. Computer are electric wires and circuits that carry all
today actually deals with zeros. Or you may have seen scary-looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only two options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1st position, the 2nd position, the 4th position, the 8th position, and so on. For example, the number 9 in binary is 1, 0, 0, 1. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only 1s and 0s, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers.
Everything can be represented with zeros.
Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. A could be 1, B could be 2.
1 is in the 1 position, isn't it? The 2 times 1. 3. 4 is in the 4s. 0, 0. 5, 6. 7, then is 8.
And so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on the screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number.
What?
This way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
This video is actually really good. Next article. What's a bit in a single bit? Can be represented 2 different values, never much 1s and 0s, off or on. Is a light bulb on or off? Is a button enabled or disabled? Is the current time AM? Okay. Username, which setting? let's learn in NoTab. Let's read on that. A computer information travels into wires, okay, on or off. An on wire represents 1 and an off represents 0. A small piece of information is called a bit. The more wires, the more the bits. A single wire can only represent 1 bit. One piece of information, we can represent the results of a coin flip with a single bit, saying that O represents tails and 1 represents heads. But we usually need to represent much more information in that computer. The solution, more wires, wire. So, 3 labels, on or off. In computers we use bits to represent numbers using the binary system behind the abstraction. In actuality, the wire isn't exactly on or off. It's an abstraction that simplifies the details of how computers work. We use abstractions often in computer science that we can easily more understand in systems that we're building. Let's peek behind the hood and see how this abstraction works. A wire can have varying amounts of electricity flowing through it, but the computer needs to be able to interpret the electricity in a wire as either 0 or definitely 1. Transistors, a tiny physical device that acts as a digital switch. In computers, a transistor turns on when enough electricity flows and stays off otherwise. How much electricity is enough? That depends on the transistor and its threshold voltage. An engineer uses a transistor with a threshold voltage of 4.5 volts, and then any voltage of 4.5 higher, the transistor will turn on. Wow, I did not know that. Otherwise, the transistor stays off basically, so 5.5, 4.5, or higher. Okay. This is off. Oh, okay. Consider a computer that needs to determine whether a USB cable is plugged in. When you plug in a cable of a mouse in the computer's USB port, circuitry in the mouse uses the voltage provided by the port to pull the voltage in the cable above 3.3 instead the computer detects high voltage. Translated on or 1. This bit information tells your computer. Oh, okay. In case engineers use the transistor with the threshold 3.3 for on state and 3.3 off the off state. A huge variety of transistors. Engineers use transistors that best fitted for the job, considering characteristics like the threshold voltage, material, and size. Transistors inside your computer are so small, we would need a higher powered microscope to see them. However, transistors are also used in other electrical projects. This is the ones you can pick up. Wow, pretty smallish or big. A lot of electrical engineer and physics goes into the physical construction of computer hardware. Like transistors, we're not going to dive deep into that. If you'd like to learn more, check the transistor works. Oh my god, let's check it out. Oh, it's a video. Okay, let's watch it.
So this right here is a bipolar junction transistor, which is a pretty common kind of transistor. And this particular one is an NPN transistor. And so this transistor is made up of 3 layers of silicon, like this. And maybe you can guess what it means for it to be an NPN transistor. These 2 layers of silicon are N-type, and this layer here is P-type, NPN. And if you haven't watched my previous video where I go into quite a bit of detail about
There's
what
3 pieces of silicon. 3 layers
layers of silicon, like this, and maybe you can guess what it means for it to be an NPN transistor. These 2 layers of silicon are N-type, and this layer here is P-type, NPN. And if you haven't watched my previous video where I go into quite a bit of detail about what these N-type and P-type silicon is. You should definitely go back and watch that. Otherwise, the rest of this isn't going to make a whole ton of sense.
Oh,
And so this is an NPN transistor, and they make PNP
he said
transistors
it's not
as well.
gonna
We'll
make
just talk about
sense.
NPN for now. And so this here is the
What you
circuit
mean
diagram
by
for a
that?
transistor, and it's got the 3 leads coming off of it. There's a emitter, a base, and a collector. And if you look at the actual physical transistor, there's 3 leads coming off, and this is the emitter, the middle one is the base, and this is the collector, although that's not really standardized, but in this particular case, that's how it works. And what a transistor does is it is a current-controlled switch. And so what that means is that if we establish a small current from the base to the emitter in this direction, the transistor will switch on, and it will allow a very large current to flow from the collector to the emitter. And sometimes you can also use this as an amplifier because a small current is amplified into a large current flow here. And so first off, there's actually something kind of confusing about the way this diagram is drawn with this arrow like this, which is that in the circuit diagram, and a lot of times, a lot of engineers like to think about positive current flow, which is current flowing from positive to negative, when in reality, it's the electrons that flow from negative to positive. And it doesn't really matter which convention we use because, as long as there's current flowing in one direction or the other, the current will have the same effect. But when we start to actually look at what's going on inside the transistor, it's easier to think of this in terms of the direction that the electrons are flowing instead of the conventional direction. And so really what's going on in here, even though the arrow is pointing this way and we think of current flowing that way, in reality the electrons are flowing from the emitter to the base. And so we'll just turn all of this around for this discussion here. And so to kind of restate what it is that the transistor does, in terms of electron flow, is that a small flow of electrons from the emitter to the base will turn the transistor on and allow a large flow of electrons from the emitter to the collector. So if we look at it,
So Brody just confused me.
this scenario,
And Brody's
piece
yapping again. Now we're gonna have to watch this on a different video because I don't understand nothing he's saying. Electron ready to bits. Question. Let's go. Okay. Alexander's putting together a simple computer machine using 2 wires. Each wire considered on and off. Okay, how many bits? 2 to the 2, right? So would it be 4? Am I tripping? Oh, not quite. So there's 2 here, and then there's 2 here. Oh, 2. It's 2 each, 1 each. Which guaranteed. Okay. Next question.